In this last lecture for Unit 5, we are going to focus on the electrolyte and acid-base balance. So in this part, for the electrolyte, we are actually going to combine the electrolyte absorption part in the reabsorption part in chapter 24 and talking about the balance, regulated balance in chapter 25 together. Well, let's first review some concepts, right? What is electrolytes? Right, electrolytes, if based on the name, so that's they are charged, right? Then why they are charged? How do we produce those particles that substrates that are charged? Well, if you kind of still remember in AMP1, we talk about when substances right dissolve in water. There are a few things can happen, right? If it's salt or acid and bases, they do not only dissolve, they actually dissociate into cations and anions. And so they basically essentially form electrolytes. That's how electrolytes are formed. They're basically pulling apart, right? And then form, hydrogen molecules with hydrogen bond with the surrounding water molecule. Well, if it's not, if it's then you also have polar substances such as glucose and urea that won't dissociate. Those tends to be organic, molecules that they just dissolve. They form hydrogen bond with the surrounding water molecule, but they wouldn't dissociate. So the major, this is looks familiar, right? We talked about this in the last lecture, talking about the major cations and anions in the SAF versus ECF. And so they are major difference in the composition of the electrolyte in those two compartments. So you kind of have to memorize what are the major ones, right? Major cations in each compartment and major anions in each compartment. Briefly, I want to kind of point to a couple things in this graph, right? Sodium here is the principal cations in this ECF. And not only that, tends to be in in our body, water tends to follow the direction of the sodium movement. That's because our body membrane tends to be the selective semi-permeable kind of membrane. The movement of the cations, right, or the ions, electrolytes are not freely. They so oftentimes then you have water movement to kind of to counterbalance the differences in tonicity, right? So that's generally principle because the most dominant ECF cations is sodium. Water tends to follow the sodium movement. Then the other cations, principal cations in the ICF, right, in the intracellular fluid is potassium. And so, but we also have a fair amount of magnesium in the ICF too. But the principal ones, the most important one is the potassium. So that's those two are the one we're going to focus on when we're talking about electrolyte reabsorption as well as balance controls, how to regulate the balance, electrolyte balance, right? Then chloride is the most abundant anion, right, in the ECF. So that's something you also might want to remember. There's a couple things I want to mention. You can see this phosphate. We have a lot of phosphate as anion in our intracellular, right, fluid. That's actually forms. That's why we have so much phosphate. Well, part of it is we use phosphates are groups different, with different hydrogen molecule as to it and as a buffering system for our ECF. And we do have a lot of, say, the ECF, right, have a lot of bicarbonate as anion. Then we actually use, that's because we use bicarbonate as a buffering system for the ECF compartment in the blood plasma as well as the interstitial fluid. So that's kind of how you can remember, okay, where can you find them? The buffering system our body use, we're going to talk about at the end of the chapter. Hopefully you can make the connection and use that knowledge also to memorize which ones, right? Which one of those electrolytes are in the ECF, which ones are in the ICF. So when we talk about electrolyte balance, it's just like when we talk about the fluid balance. We're talking about to get to balance, right? You need to have the input equals to the output. So then how basically the input comes from food, right? Because those are electrolyte we cannot generate them ourselves. But then food and drink, and then then what's the output? So output is mainly through sweat, right, or through urine, and so therefore the reabsorption, right, of those electrolytes in urine is a major process to maintain this balance. So if you have, basically we want to have regulate the reabsorption of the electrolyte to make it in urine, in kidney, right, to make it then equals to the input. Let's first use sodium balance as an example, right? So here, right, to maintain the balance on the intake part is from the diet, food and water. On the output part, we have the sweat, feces, and urine. Right? Sweat we can't really control, feces we can't really control, but we can control the most regulated part is from urine. The sodium, how much we actually reabsorbed from the urine, is under the control of 3 hormones. Okay, so aldosterone, ADH, and AMP. Does it ring like a ring for you, right? So ring a bell for you. That is actually the 3 of the 4 hormones that we talk about at the end of last lecture that involves in regulation of the urine output. Right? Let's look at briefly how each one of them is going to, how each one of them regulates sodium and balance, right? Or reabsorption. So actually, the aldosterone here, right? It retains sodium and water, and the ADH only retains water, has no control over actually sodium directly, right? But because it retains water, so then the result would be to decrease the sodium plasma concentration, right? Even though it doesn't really directly influence the sodium that we lose in the urine. On the side of the AMP, if you remember, that AMP is always, promoting the opposite reaction, right? Almost always opposing aldosterone and ADH. So that one actually increased the excretion of sodium and water. Right, so this is directly opposite of aldosterone. We're going to talk about how they do that in the next slide, but generally, right, if you have the SAF, that's the cell, right, you have the ECF, that's the interstitial fluid and blood plasma, right. If you have decreased water or increased sodium concentration in the blood plasma, and then it basically means the blood plasma is hypertonic. Then you would have water moves to where the sodium concentration is high. right? So that's water movement by osmosis. And that's how sodium actually concentration regulates the fluid balance. Not only, have effect on the electrolyte concentration, but regulates the fluid balance. When we talk about fluid balance, we are talking about water movement, right? And so the opposite is also true if the blood plasma become hypotonic, right? Either because it's too diluted or because of the sodium is low, right? And then you have the water move again to move away from the hypotonic compartment, then to the more hypertonic, right? So then cell, in contrast to the blood plasma, is then hypertonic, then the water is going to move into the cells. So that's kind of the fluid balance we talk about. Then let's look at how the sodium is get reabsorbed in the kidney. So about 75% of the sodium reabsorbed in the PCT. Remember, we saw the PCT is where most of the substances, including electrolytes, are reabsorbed. They have a lot more microvilli on their membrane, right? Than the other parts of the tubules. So, and then about 25% of them are reabsorbed in the nephron loop. Remember, the nephron loop, you have, the permeability to the water and the solids, kind of take turn, right? On one side is permeable to the water. On the other side is permeable to the solid. And so through that mechanism, a lot of the sodium can also be reabsorbed. And then the last part, if you add that up, about 10%, right, of the sodium, then is going to be reabsorbed in the DCT, as well as CT, that will be collecting tubule, and CD meaning collecting duct, right, the distal portion. And that's 10%, roughly 10% is the regulated portion. So basically, the first, right, 90%, we're going to kind of reabsorb them, kind of distinguishedly, right? But then the last part is going to be regulated based on your body's need. And how the sodium gets, the first get non-distinguishably be reabsorbed. So it's basically diffusing because in the PCT, right? Initially, you have those are tubular fluid on one side. You have the blood flow on the other side, right? So it's diffused. They have to get across the tubule cells and then move. Then against this concentration, gradients has to be pumped out by the sodium and potassium pump, right? Then to the interstitial fluid, then going to diffuse into the blood. And that's how what happens in the PCT. What happens in the DCT, more the distal end, is again you have the tubule fluid on one side, you have the blood flow on the other, right? The cells are involved here in the distal portion of the nephron, right? It's actually called principal cells. You're going to see these cell names a couple times more, but this is the first time you see that. They're called principal cells. What they have is they have sodium channels, right, on the lumen, facing the lumen of the tubule, and then they have the sodium potassium channel. I mean the pumps, right, on the side facing the interstitial fluid, and so that's still the same mechanism how they used to reabsorb the sodium in the PCT is how they're going to reabsorb in the DCT. However, but then you can see how the sodium reabsorption is basically depending on the number of the sodium channel on the lumen side and the number of the sodium potassium pumps, right? The more sodium channels they have, and the more sodium potassium pumps they have, then there's going to be more sodium. There are going to be more sodium going to be reabsorbed, and because of the work of the sodium potassium pump, there is actually moving the sodium to one direction and the potassium to the other. And so if you have this pump works, it's actually moving sodium into the blood, but also at the same time moving the potassium, right, into the opposite direction, into the tubular fluid. So you're basically having sodium reabsorption and potassium excretion, right? So secretes potassium out, excreting the potassium out happen at the same time. So how the hormone comes into play here then? Aldosterone here, right? That's the molecule, that's the hormone secreted from your adrenal gland, right? So that hormone is going to act on the principal cells, increase both the number of the sodium channel as well as the number of the sodium potassium pump. So basically, if you have aldosterone, you're increasing the sodium reabsorption, you're also increasing the potassium excretion or excretion. And we talk about how water generally follows sodium, right? So if you increase the sodium reabsorption, you increase the water reabsorption, and the water is going to get in through the water channel proteins are called aquaporin. Because water, if you for the large amount of water, secretion, reabsorption, you need water channel too, and they are, remember, the same, aquaporin, right? So that's the water you basically increase the water reabsorption, and when you increase both sodium and water, you increase reabsorption, you increase the blood volume, and you decrease, right, because more of them are getting reabsorbed, so then you decrease the urine output. And the net result of this, of course, is what in terms of the blood pressure? That's increase your blood pressure. So that's how one of the mechanisms of aldosterone, right, increase blood pressure. And then how does then AMP work? Well, AMP actually inhibits the action of aldosterone. So it's inhibit aldosterone, then it inhibits the whole process, right? But in addition, AMP also inhibits the sodium reabsorption. The default one happens in the PCT. So AMP inhibit that reabsorption. So generally, then speaking, and taking together, not generally, but taking it together, then AMP inhibits sodium reabsorption, then inhibits the water reabsorption, right? So if you have less reabsorption of sodium and water from the tubular fluid, the end result is you have more urine volume, right? So the urine output is going to increase, then your blood volume is going to decrease, then you have a lower blood pressure result from AMP. And how about then water reabsorption? Similar to the sodium, you also have 75% of them, right, reabsorbed in the PCT, about 10%. You can see the number of 75% is actually pretty consistent throughout all different substances we talk about here. So 10% of the water absorption in the nephron loop, right? And then the last part, similar to the sodium, is happening in the distal portion of the nephron, and that's where the regulated, right, the facultative water reabsorption happens. So that means it depending on your body's need, right, and then how much water gets reabsorbed. deciding how much water gets reabsorbed. The major molecule that, in addition, so we talk already about how the water follows sodium in the last one, right? So that means aldosterone would have a influence on the water reabsorption because it's influence sodium reabsorption, therefore influence water reabsorption. But in addition, you have ADH, so that is antidiuretic hormone ADH that's secreted by posterior pituitary gland. Remember that? We learned about it in the endocrine system. And that hormone promotes the water channel. So remember this water channel aquaporin, right? That is actually in the number of aquaporin is increased by ADH. So ADH, if increase the number of water channel, therefore increase the water reabsorption, right? Because that's the more you have, there's the osmosis, the difference in the concentration, right? In the osmolarity going to push the water in. I mean, so that's water always also come in, but depending on how many water channels you have on the principal cell, again, it's principal cell that's going to decide how much water going to be reabsorbed. So ADH only actually affects the water reabsorption, has no effect on the sodium. But then the more water gets reabsorbed, then it's still the same thing. You have increase in blood volume, decrease in urine output, right? So the blood volume and urine output is always on the opposite side. If you have increased blood volume, you always have decreased, right? Urine output. Then that's going to again result in increase in the blood pressure. Well, there's this condition, right? When you have lower than normal ADH, right? Or sometimes it's just, your principal cells of the kidney are not responding to ADH, right? Either way, you have a low ADH, or that either way is going to result in low number of aquaporin on the principal cells. And what's the result of that is that you're going to lose a lot more fluid, right? Especially water component in your urine. And if you still remember the number we talked about last time, in your body daily, your nephron filtrate generate 180 liter of filtrate. But then most of that, of course, a super majority of that gets reabsorbed. But if you have, like ineffective, basically mechanism of ADH regulating the water reabsorption, you can lose up to 20 liters of fluid daily. Compared to normally, our urine output is only between 1 to 2 liters. So that means this condition, diabetes insipidus, basically results in dehydration, right? Because you're losing a lot more water, not only fluid, but a lot more low concentration, like solids out. So it's going to change the tonicity of your blood, of your body fluid, and so that's dehydration. Then let's look at how about the potassium, right? Potassium is, if you still remember, say the normal total range is very, very low in the EC. This is only in the ECF we'll talk about. So it's normally really low in the ECF, but very highly, most abundant in the SAF, right? Again, the intake is from diet, the output is from urine, feces, and sweat. While hormone can also regulate potassium plasma concentration by this aldosterone we talk about, right? Because aldosterone regulates increased sodium and potassium pump, and that means it not only increased sodium reabsorption, but at the same time actually increase the secretion of potassium. So more of the potassium going to be lost in the urine, right? And then you have decreased the potassium blood plasma concentration. So only one of those three hormones involved in the sodium reabsorption are involved in the potassium, and it's actually through the same mechanism. So because of our cells have much higher concentration of potassium, and there's, if you remember, also 2/3 of the body fluid is in the ICF. So if to maintain normal potassium blood levels, if there's any change in the blood potassium blood volume, then basically the ICF, the cells, are going to serve as kind of a reservoir, right? And so if the blood potassium increases, then the potassium going to enter into the cell. If the blood potassium decreases, then the potassium is going to come out of the cells. So then to keep the blood plasma potassium constant. It's low, but it is important. It is low compared to sodium, but it's still important to keep the potassium blood level normal. So that's the only one we're going to focus on today. Of course, but the other potassium can also actually help in maintain blood pH, and even there are situations after a meal. But we're not going to actually spend too much time talking about that. But just know the cells works as a kind of a reservoir going both ways, right? Help regulating potassium blood level. Basically extremely low potassium level in the blood, called hypokalemia, is actually potentially lethal. But then extra high potassium level is also lethal. It can be used actually potassium as in some states be used as a lethal injection, lethal execution agents, because high dose of potassium can stop your heart, because of the importance of potassium in the neuron physiology. This looks familiar again, right? If we look at where the potassium gets reabsorbed, again, 60 to 80% of them happen in the PCT, and about 10 to 20 in the nephron loop. Then the last part, the regulated absorption, reabsorption, and the secretion always happens in the collecting tubules and the most distal part, right? And again, it's through these principal cells, depending on the aldosterone level. Well, then let's look at another cation that's important in our body, right? So that's actually together calcium and phosphate balance. So if you still remember from AMP, the blood calcium level is actually can be influenced by many hormones, but we talk about parathyroid hormone being a major one, regulating blood calcium level, right? How do they do that? We we said, well, it's influencing the calcium, right? Reabsorption in the kidney, and this is where we're going to actually talk about it. So in addition to influencing to promote the calcium reabsorption, but also at the same time, PTH decreased phosphate reabsorption, because if you have both calcium and phosphate, they tend to be then deposit at the bone and to make bones. If you really want to increase the blood calcium level and to decrease, at the same time, to prevent it from just being carried to the bone and deposited at the bone, you actually at the same time want to decrease the phosphate reabsorption. And so then the ratio of the calcium and the phosphate changes, more of the calcium stays in the blood. And so PTH actually inhibits the reabsorption, right, of phosphate in the PCT, because most of the reabsorption happens here. It inhibits, lowers the phosphate reabsorption there, but at the same time stimulates reabsorption of the calcium in the DCT. So it has two acting sites and working on two different electrolyte. So that's the result is then you have increased, right, phosphate loss in the urine. So then increased blood calcium level.